Okay. So in this problem, we're kind of introducing a different way of solving them. We're still doing upwardly launched projectiles, but again, in this one, we're working kind of backwards from what we've done in the past. So it says an object is launched at an angle from the ground. It reaches a maximum height of 45 meters, and then it returns to the ground after a horizontal distance of 240 meters. So that's its range. Find its initial velocity. So the initial velocity, again, is normally what we're given with initial velocity and an angle and so forth, and then we have to, solve for the components and whatnot. But in this problem, it doesn't give us that. That's what we're trying to find. So it gave us the range and the height, and so we're going to use that information to solve for the initial stuff. Now, we need to think about too. Really, almost all these projectile motion problems involve us looking for time, and that's what we're going to be needing to do. So we're going to have to find time. Let's think about the horizontal distance being 240 meters. So horizontal distance is really again determined by the horizontal motion, which is constant motion, not accelerating. Velocity equals distance over time. We know that the distance is 240. So, and we're really trying to find is the velocity in the x direction. So we know that the distance is 240 meters. But again, I think you'd realize right there that this problem is going to hinge on time because we don't have it there. So again, we could solve velocity in x, but we don't have time. So the next thing we're going to do is really going to think about the time. The time is always going to be determined by your y component. And here we have a height of 45 meters. That's all it really gives us. We also would know, hopefully, that it's gravity. Gravity is negative 9.81. And so we have like two pieces of information. But two pieces of information isn't going to be enough to solve for time. If I go back to previous equations, I've got to go back a little bit in our notes. Here we go. Um, we have to use one that has time in it. And remember that we have acceleration and distance. So which equation is going to allow us to solve for that, Hannah? I would say the second one as well. Okay. So I would say the second one is definitely the best choice, but I think we're going to have to realize that what we need to do to it. So let me go back and let's copy it down. The distance vertically, say the distance in the y, displacement in the y, is equal to velocity initial in the y direction times time plus half at squared. Or let's do gt squared. G is gravity. So again, we have the displacement in the y direction. It's 45 meters, right? So, but I guess we need to think about that a little bit more. And we also have g, which is negative 9.81. So the distance in the y direction is 45 meters. But is that the distance that it travels totally in the y direction? No. What does it do? Goes up and comes back down, right? So it covers a total of 90 meters total. 45 goes up and comes back. Yes, it does it twice. So it goes up and back down. But I would also say that we can't use it that way. Now, here's why. If we use 90 meters, again, the projectile goes up 45 meters and comes back down 45 meters. But what that would allow us, what that would entail us to do is we'd actually also have to have, so we're trying to find time, remember this. So it also entail us to have an initial velocity. So we would have to have an initial velocity to be able to solve that. So we'd put 90 in, 90 equals velocity initial times time plus half of negative 9.81 times t squared. And we wouldn't have an initial velocity. That's, again, we want to solve for time, but we also need to eventually solve for initial velocity. But if we think about it in a specific way, we can get initial velocity to cancel out. And that's what we have to do. Okay. In what situation would initial velocity cancel out? Nope. Try it again. When it's just going down. The initial velocity when it's at the top and falling down is going to be zero. At the top of its motion, its initial velocity in the y direction is zero. And so that cancels out. And if that cancels out of our problem, that allows us to solve for time on the way down. Okay, and so that's what we have to do. So the distance in the y direction is 45 meters. It's negative because it's going down. We're just focusing on the down portion. Again, initial velocity cancels out in our problem, equals half of negative 9.81 times t squared. Okay, now we can solve for t. So 45, 4.6, um, sorry, 9.2 equals t squared, and then we square root both sides, and we get a time of 3 seconds. Just gonna keep it three. Oh, that's not an answer. I'm sorry. I just boxed it anyway. Too late. So does that make sense though? We solve for time. This is time going down though, not time entirely. So imagine again this twice the time it would take to go up and back down. Okay, so that'd be 6 seconds. Let's go ahead and plug that in over here. Um, in the x direction. So 240 divided by the total time of 6 seconds gives us a horizontal velocity of 40 meters per second. So velocity in the x equals 40 meters per second. That is one of the components then of our velocity vector. So one of the components of our velocity vector. But like I said, it all hinged on time, but we also need the velocity in the y direction as well. And now that we have time, we can use another equation to figure out the y velocity. Um, so let's do that, I guess. The initial y velocity. Um, again, we have lots of pieces of information now, but I think the easiest equation we could use, velocity final equals velocity initial plus acceleration times time. That would allow us to figure out, again, the velocities. Um, depends how you want to think about it, but I think the easiest way to think about it is to think about the velocity going down. Go ahead. It doesn't really matter. Yeah, you just can't think about it as the whole entire motion, right? You could, but it would make the math a little bit harder. So the easiest way to do it is to really try and get one of these final velocities or initial velocities to be zero. So okay, if we think about it as going up, the final velocity of the y direction at the top would be zero because at the top of its motion it reaches 0 meters per second in the y direction. We're looking for the velocity initial, and then the acceleration is negative 9.81. And the time to go up is just 3 seconds. So we want to use 3, not 6. So yes, it comes out to be what, 27? 3 times 9.81, 29. Sorry, thank you. 29.4. So the velocity initial equals 29.4 meters per second. That would also again be the final velocity on the way down as well, but that would be negative. So either way. Okay. Well, you're probably like, oh, I wish we were done yet, and I wish we were done, but we're not. The initial velocity is the combination of your x and your y. So 40 meters per second, 29.4, which we just solved for. So again, we have our x and y components. We needed to solve for the hypotenuse and the angle. So now it just comes down to trigonometry. 40 squared plus 29.4 squared, and the square root of that. We get a hypotenuse of 49.6 meters per second. That is one of our answers. We also need a direction as well there, so we need the angle at which it was launched at. And to do that, I think the best thing is tangent, but you could use any trig function at this point in time. And we get an angle of 36 degrees. Also another answer. 36 degrees north of east. So we worked it backwards. We had the range, we had the height, we were able to work it backwards and solve for the initial velocity. And it all hinged on time. Most of these problems are all going to hinge on the time that it takes. Cool? Okay, so let me give you one more example problem, and we'll see that there is a problem with it that we've got. So let's take a look at it. So a daredevil jumps a canyon 12 meters wide. To do so, he drives a car up 15-degree incline. A car. Yeah, I guess we could say a motorcycle, but he's jumping into a car. I mean, it's no big problem there. It says, what minimum speed must he achieve to clear the canyon? Okay, it's really kind of like the last problem where we're finding the initial velocity. Let me read B as well. If the daredevil jumps at this minimum speed, what will his speed when he reaches the other side? Now, this is an A and B problem, but is it really different? No. Why? Maybe. Maybe. It's not. No. Anybody have an answer on this one? You've said a lot of the answers. Okay. The A and B are really the same question because think about it. The projectile goes up. In this case, it's a car, and it has some initial velocity. But as it comes back down, that final velocity is the same. So the only thing that's going to be different is this is going to be a positive velocity, and this is going to be a negative velocity. So I think the first thing to realize in this problem is it's not two separate problems. You're going to solve the answer, and then to get B, you put a negative sign in front of it, and you got the second answer. Okay, does that make sense? Yes, Mr. Duffy. Thank you. Okay, cool. Okay, now what also is different in this problem is that it gives us a range, the width of the canyon, and it gives us an angle, but that's it. Okay, so let's draw a diagram. We've got ourselves a canyon, and the car is going to drive off a ramp, and it's going to go 15 meters, or sorry, 12 meters across the canyon. Sorry, I keep writing 15 because it's a 15-degree angle, but 12 meters, it's a 15-degree angle. Now, this could be solved with trigonometry and substitution of different values of the velocity and the x and the y and so forth. But it's really quite difficult to do it that way. It really is much easier, and I would encourage you to do it with a new equation that I'm going to give you. It's called the range equation. The range equation kind of like substitutes in some of these basically it again does the legwork for solving like the y velocity determines the time. It kind of just like puts everything together into one nice neat package to figure out how far something's going. We know that the range of an object is determined by the velocity in which it goes and the angle at which it launches at. It's also determined by gravity as well, but normally gravity is negative 9.81. It's not always, but again, normally it is. So the range equation is velocity initial squared. I use this. I know. I use this one time a year. Sine 2 theta over g. Okay. You can use this on lots of different problems. So again, I would encourage you to use it. It does make a lot of problems a lot easier, but I guess you would also need to be able to solve them the way I've previously taught you them as well. So, for example, if we had like a golf ball being hit down range or something like that, and you want to figure out how far it went, you can use this equation, and it's very easy to solve for the range. But if a problem asks you more than that, like the time required, how high it goes into the air, those things you're going to have to solve out separately. And so again, it's a good tool, but you still need to know the other stuff that I've previously taught you about how to like resolve the vectors into x and y components and then use the kinematic equations. But in some problems, you cannot do that. like in this one again, we don't have enough information to solve for it easily, and so the range equation becomes the best option to figure out how far, um, or figure out like how something was launched. Okay, so the range in this problem is 240, or sorry, the last one was 240 meters. This one's 12 meters. The initial velocity is what we're looking for, so we're going to leave that blank. Sine of 2 theta, the angle basically. So sine of 2 times 15, which will be 30. We could just type it in as 30 in our calculator. I would encourage you to do that. And then divided by negative 9.81. Okay, so now again, what we can do is figure out the initial velocity in which the car launched at. So let's see, just algebra. 12 times negative 9.81. It's 117.7 equals velocity initial squared sine of, again, I would encourage you to do 30 degrees, because if most people do this, they do sine of 2 and then times it by 15. But again, that that uh, that would get you the wrong answer. If you type it in your calculator right with parentheses and stuff, then it would work out. But most people just don't do that. So it's better to just enter sine of 30. Okay, so 117.7 divided by the sine of 30 is 235, and we need to square root that. 15 meters per second. That would have taken half an hour to do otherwise. Okay, you would have had to solve for the velocity in the x and the velocity in the y using like components, but you wouldn't have numbers to again solve it. So you'd have to like rearrange and then see what stuff cancels out and what does not cancel out. And again, it would have taken a lot longer. The range equation allows you to again to solve for how fast it's going very quickly. Okay, so I would encourage you to use that as a very nice tool